Hello fellow programmers. Today I want to teach you the Sprague-Grundy-Theorem. This is a continuation video from my first game theory video. I will quickly do a short recap, but if you haven't watched my last video, then check it out to get a better understanding of the subject. All the theory I will talk about in this video will only apply to impartial combinatorial games. But now let's get started. For the recap, I will introduce a very simple game. It's a very popular game in game theory. It works like this. We have 7 blocks and 2 players, and in each move a player can remove 1, 2 or 3 blocks. And the last person who can't remove any blocks loses. In the last video I've talked about the winning and the losing states. And here's just a reminder. A state is a winning state if at least one move leads to a losing state. And a losing state is a state where no move leads to a losing state. So if we analyze our game, we get the following winning states and losing states. If we have 0 blocks, then this is clearly a losing state. If we have 1 block, then we can remove the block and we end up at a losing state. So this is a winning state. If you have 2 blocks, we can remove both blocks and end up with a losing state. So this is also a winning state. The same if you have 3 blocks. But if you have 4 blocks, then if you remove 1 block, we end up in a winning state. If we remove 2 blocks, we end up at a winning state. And even if we remove 3 blocks, we also end up at a winning state. So we can't reach a losing state. So this must be a losing state. And then if we quickly fill out the rest, 5, 6, 7, they are all winning states. Because you can reach the state with 4 blocks. Okay, this was quite easy. Now I want to extend this definition a little bit. For this I define the Grundy values, or also called the numbers. The number is defined as the max of all reachable number values. So we try out every move, take the number values of those states and compute the max. Be careful, this is not the maximal number in the list, this is the max, which stands for minimal exclusion. The max is the smallest non-negative number which is not in the list. So let's quickly compute the number values of our game. The number value of 0 is the max of all reachable number values. If we only have 0 blocks, then we can't remove any. So we can't do any moves. So this is the max of the empty list. And the smallest non-negative number that is not in the list is 0. Now let's compute the number value of the state with 1 block. From 1 block, we can go to a state with 0 blocks. By removing the only block. So we end up at a state with the number value 0. So what is the smallest non-negative number that is not in the list consisting of 0? It is 1. From the state with 2 blocks, we can either reach the state with 1 block or with 0 blocks. So we have the max of the number values 0 and 1, and the smallest number that is not on the list is 2. In the same way, we can compute the number value for the state with 3 blocks. We can either reach the state with 0, 1 or 2 blocks. So we have the number values 0, 1, 2, and the max of them is 3. So far these values are really boring. But now it gets more interesting. If we have 4 blocks, we can only reach the states with 1, 2 or 3 blocks. So these are the number values 1, 2 or 3. And now the smallest number that is not in the list is 0. For 5, it is the max of 0 to 3, because we can reach the state with 4 blocks, which has the number 0, or we can reach the state with 2 blocks, which has the number 2, and the state with 3 blocks, which has the number 3. And here 1 is the smallest non-negative number that is not in the list. And in the same way you can compute the numbers of 6 and 7, which are 2 and 3. It's quite often that these number values have an easy pattern. So in this case, it's just 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and this will repeat and repeat and repeat. But this doesn't have to be the case. Now, one important property of these number values is that if the number value is 0, then the state is a losing state. You can see here the number value 0 is a losing state, and here the state with 4 blocks, which has the number 0, is also a losing state. And all the other states, so all states with a positive number, are winning states. And this is actually quite logical. If you are on a winning state, so you have a positive number, then you can reach a state with number 0, because otherwise the max would have been 0 itself. So from a winning state, you can reach a losing state. But if you are on a losing state with number 0, then you can't reach another 0. Otherwise the max would have been positive. So from a state with number 0, the losing state, you can't reach another losing state. Now I want to do a little bit different. Instead of playing one game with 7 blocks, we play multiple games at the same time. We play the game with 7 blocks, then we play a second game with 5 blocks, and then we play a game with 4 blocks. And the rules are very similar. You can remove 1 block, 2 blocks or 3 blocks in each move, but you only can do this only from one of the game boards. So in the first move you can remove the first 2 blocks of the first stack, the second player removes 1 block from the third stack, then you as the first player remove the remaining 3 blocks from the third stack, then the second player removes 2 blocks from the first stack, and so on. And the end is similar. The last person who can't remove any blocks loses. And now we have a problem if we use the old definitions. This is still an impartial combinatorial game, but we have a lot more states. Actually, we have exponential many states now. So the computation of the winning and losing states will be very, very expensive. So the computations of the losing and winning states will take a long, long time. But here is where the Sprague-Grundy-Theorem comes to shine. The theorem says the number value of the sum of multiple games is the same as the XOR of the number values of the individual games. So here we have 3 different games, one with size 7, one with size 5, and one with size 4. The number values of the individual games are 3, the number value of size 5 is 1, and the number of size 4 is 0. And so in total we have the XOR of 3 and 1, XOR with 0, and this is 2. So the number for the combined game is 2. So we know this state is a winning state. And if we play optimally, we will win the game. How do we win? Well, exactly as the definitions, we have to make a move so that the other person ends up in a losing state. So we want the XOR sum to be 0. And we can accomplish this just by removing 2 stones from the first pile. This way the first block has the number 1 and the XOR sum is 0. So now the second player is in a losing state. It doesn't matter what he does. For instance, he can remove 3 blocks from the second pile. This will give a number value of 2 and an XOR sum of 3. But still, now this is a winning state, because the number value is positive. And since the number is positive, you can make a move so that the number will be 0, and that the second player ends up in a losing state. So in this case, for instance, there are many options. We could remove 3 blocks from the first pile, or 1 block from the second pile, or 1 block from the third pile, which I choose the later option. This will give the number 3, and in total we have the number 0. So the second player is in a losing state. He removes both blocks from the second stack, which gives a number of 0 and in total 2. You remove 2 blocks from the first pile, which gives the numbers 3 and in total 0. The second player removes 2 blocks from the first one. You remove 2 blocks from the last one, again leaving a number of 0. And then the second player is forced to take 1 block, and you can remove the last block and win the game. That's basically all it is. You compute the number values of each of the games, take the XOR sum, and then you get the number value of the combined game. In our example, we had 3 very similar games. They were just different because we started with different heights. The first with 7 blocks, and the second with 5 blocks, and the third with 4 blocks. But this can be actually quite different games. For instance, we can combine the game with the 7 blocks with the chess problem from the previous coding exercise. Compute the number values of both games and XOR them. And it still works. So it isn't actually important what games you play, just to take the XOR sum. Now I want to present the proof of the Sprague-Grundy-Theorem. You don't need to understand the proof to use the theorem. It's quite a nice proof, so I want to show it, but you don't actually need to understand it to apply and use the theorem. Everything you need to know to use the theorem, I already told you. For this proof, I have to show that this number, this value, actually satisfies the definition of the number. So we have to show that this actually satisfies the definition with the max. And I will do this with 2 steps. Let's define this as b. So in the first step, I have to show that for each value a that is smaller than b, there's a reachable state with the number a. So in the combined game that has the number b, I can do a move to reach a state with number a. And in the second step, I have to show that I cannot reach a state with the number b. If these 2 conditions are true, then the number of the combined game is really b, because it satisfies the condition using the max. The max is the smallest non-negative integer that is not in the list, and so each number smaller than the max has to be in the list, and the max itself is not in the list. So let's start with the first condition. We first look at the XOR of a and b. This is obviously a positive number, so if we write it in binary, the number will start with a 1. This resulting number has k digits, so the digit at the position k is a 1. Now because a is smaller than b, this also means that there has to be a 1 at the position k in the binary representation of b. And because b is the XOR of all number numbers, at least one of the numbers of the individual games also has to have a 1 at the card position. With a loss of generality, we can say this is the game G1. So the number of G1 has a 1 in the binary representation and exactly at the position k. But now this means that a XOR b with the number of G1 is definitely smaller than the number of G1. And so there exists a position G1 tilde that you can reach from the game G1, and this state G1 tilde has the number value of A XOR B XOR N of G1. And this is also the move that we are going to make in our game. Our game is the combination of multiple games, GI. And we're going to perform this move, and we will end up at the number A. Let's just prove this. So if we do this move and compute our new number with the Sprague-Grundy-Theorem, we will end up with number of G1 tilde XOR number of G2 XOR number of G3 XOR dots, all the numbers of the other games. And this is nothing else than A. If we use the definition of the number of G1 tilde, then we get A XOR B XOR the number of G1 XOR the number of G2 XOR dots, and this is just A XOR B XOR B, because the XOR of all numbers is B, and B XOR B is 0, so in total we get A. So from our combined game, we can reach every number value that is smaller than B. So this proves the first part, and the second part is really short. We want to show that we can't reach a state with the number B from our combined games. Without loss of generality, we can say that our move is from the first game. So we move from G1 to G1 tilde. This means, however, since the number of the states is defined using the max, that the number of G1 tilde is not the same as the number of G1. After this move, using the Sprague-Grundy-Theorem, this combined states have the number n of G1 tilde XOR n of G2 XOR dots. But this is not equal to the number of G1 XOR n of G2 XOR dots. And that's B. So with any move, we can't reach a state with number B. And this finishes the second part of the proof. We can reach any smaller number, but we can't reach the number itself. That's the definition of the max. And so the theorem holds. I hope you learned something new about game theory and maybe even understand the proof. If you haven't watched my last video about game theory and you have some questions about impartial combinatorial games or the winning and losing states, check out the video. And if you want to apply and practice the Sprague-Grundy-Theorem, then I will link a few nice problems in the video description. Thanks for watching.